Right now, somewhere in the depths of our galaxy, there exists a dead star barely 12 miles wide that's literally warping the fabric of reality. Its magnetic field possesses such devastating power that it can rip apart the very emptiness of space itself. In a mere tenth of a second, this cosmic nightmare discharged more raw energy than our own sun will generate over the next 100 millennia. This isn't some distant black hole we're talking about. This is something potentially even more terrifying. This is what scientists call a magnetar, an object so fundamentally extreme that it shatters every rule of physics we once believed to be absolute and unbreakable. If you're here to explore the universe's most closely guarded secrets, go ahead and smash that like button and hit subscribe, because what I'm about to reveal will fundamentally alter how you perceive that starry sky above us. Let's dive in. When a massive star finally exhausts its fuel supply, it doesn't go quietly. Picture a stellar giant that's been burning for millions upon millions of years, methodically fusing elements deep within its core, constructing progressively heavier and heavier atomic structures. Then suddenly, catastrophically, the fuel vanishes. In less than a single second, the core undergoes complete gravitational collapse. The outer layers rebound violently, creating a supernova explosion so brilliant it temporarily outshines entire galaxies. Everyone's familiar with that story. But here's what they conveniently leave out of the textbooks. Not every stellar corpse inevitably becomes a black hole. When the progenitor star falls within a very specific mass range, somewhere between 8 and 20 solar masses, something completely different unfolds. The collapsing core doesn't continue shrinking indefinitely into a singularity. Instead, it halts. It compresses down into a sphere measuring just 12 to 15 miles across, yet it refuses to vanish beyond an event horizon. What emerges is a neutron star, essentially a city-sized sphere of matter compressed to such mind-bending densities that a single teaspoon would tip the scales at roughly the same weight as Mount Everest. But certain neutron stars are born with an additional twist, quite literally. As the core undergoes this catastrophic collapse, it begins spinning faster and faster, much like an ice skater pulling their arms inward during a spin. The original magnetic field that permeated the massive star gets compressed too. Squeezed into that impossibly tiny volume, the magnetic field amplifies to levels that physics suggests shouldn't even be possible. The end result? A magnetar. This isn't theoretical speculation anymore. This is confirmed, documented science. We've successfully detected these objects. We've measured their electromagnetic emissions. And the numbers we're seeing are absolutely horrifying. A magnetar's magnetic field achieves strengths reaching 10 to the 15th Gauss. That translates to 1 quadrillion times more powerful than Earth's protective magnetic field. It exceeds the strength of a typical neutron star by a factor of 1,000. At that level of intensity, the magnetic field itself transforms into a weapon. Consider this scenario. If a magnetar somehow materialized halfway between Earth and the Moon, approximately 120,000 miles distant, it would instantly erase every single piece of magnetically stored data on our entire planet. Credit cards, computer hard drives, backup systems, everything gone in an instant. But that's honestly the least of our concerns. The real danger lies in what that field does to matter at the atomic level, because this is where the laws of physics start completely breaking down. At distances closer than 600 miles from a magnetar's surface, the magnetic field achieves such overwhelming intensity that it physically warps the geometric shape of atoms themselves. Electrons, which normally maintain spherical orbital patterns, get stretched and deformed into thin, needle-like structures. Atoms cease behaving like atoms. The fundamental building blocks of chemistry simply stop functioning normally, and we're just getting started. What happens when you venture even closer? Imagine compressing our entire sun down to the dimensions of a small city, not Hollywood's dramatized version of compression. I'm talking about real, actual physics-based crushing. Every single atom smashed together so tightly that literally no empty space remains between them whatsoever. That's what you're dealing with here. A magnetar measures roughly 12 miles in diameter. You could drive straight across one in approximately 15 minutes at highway speeds. Yet somehow crammed into that inconceivably small sphere is 1.4 times the total mass of our entire sun. This isn't speculation or estimation. Scientists have precisely measured magnetar masses by observing their gravitational effects on nearby celestial objects and analysing the frequency patterns of their pulses. The data remains consistent across multiple observations, and it's deeply, profoundly disturbing. How does this even work? In normal matter, atoms consist primarily of empty space. The nucleus occupies the centre. Electrons orbit at relatively vast distances, and between them exists nothing, just emptiness. But when a star collapses into a neutron star, gravity crushes everything together with such force that electrons get literally forced into the nucleus itself, where they combine with protons to form additional neutrons. What remains is pure neutrons packed shoulder to shoulder with absolutely zero gaps between them. This creates what physicists call nuclear density. At this level of compression, 1 cubic inch of magnetar material would weigh over 600 million tons. A sugar cube-sized chunk of this stuff would weigh more than the entire human population combined. If you somehow managed to drop a teaspoon of this material onto Earth's surface, it wouldn't just fall through the ground. It would slice through our planet like it wasn't even there, punching straight through to emerge on the opposite side. The density reaches such extreme levels that the surface gravity becomes nightmarish, beyond comprehension. Stand on a magnetar's surface and you'd experience gravitational forces 200 billion times stronger than what we feel on Earth. That's 2 times 10 to the 11th. You wouldn't simply be crushed. Your constituent atoms would be violently ripped apart and smeared across the surface in a layer precisely 1 atom thick. But even this barely scratches the surface of how strange these objects truly are. Because magnetars don't just sit there passively. Their surfaces move, they crack, they quake. And when that happens, the entire universe takes notice. The magnetic field holds the magnetar's crust in place like a massive vice. But the crust itself consists of crystalline iron, harder than diamond, floating atop a sea of superfluid neutrons. As the magnetar rotates and its magnetic field gradually shifts position, enormous stress accumulates within this crust. Eventually, something has to give. What happens next makes our most powerful earthquakes look like gentle tremors. On December 27, 2004, something struck Earth. Not physically, but every satellite orbiting our planet simultaneously detected it. Radio telescopes worldwide went completely haywire. The ionosphere, 60 miles above our heads, suddenly illuminated for no apparent reason. Scientists frantically scrambled to understand what had just occurred. The source sat 50,000 light-years away. A magnetar designated SGR 1806-20, and it had cracked. This wasn't some minor event we're talking about. When a magnetar's crust fractures, it unleashes energy that makes our most devastating nuclear weapons resemble firecrackers in comparison. The December 27th event discharged more total energy in 1/10 of a second than our sun will produce over the next 150,000 years. From 50,000 light-years distant, it appeared brighter than a full moon to our orbiting satellites. This is confirmed, documented data from NASA and multiple international observatories. Think carefully about that distance for a moment. Light travelling for 50,000 years. and the burst still arrived with sufficient strength to affect our planet's atmosphere. If this particular magnetar had been positioned just 10 light-years away, the same distance as some of our nearest stellar neighbours, the radiation would have completely stripped away Earth's ozone layer. Complex life as we know it would have ended. Period. But what actually occurs during one of these star quakes? The magnetar's iron crust, held under immense magnetic stress, suddenly shifts position. It might move less than a single millimetre. That's it, a fraction of an inch. But when you're moving crystalline iron harder than diamond, packed at nuclear density, even a millimetre displacement releases unimaginable quantities of energy. The magnetic field lines snap and reconnect violently, like rubber bands stretched far beyond their limit and released all at once. This magnetic reconnection accelerates particles to nearly the speed of light. Gamma rays and X-rays spray outward in all directions. The magnetar rings like an enormous bell, its vibrations creating pulses we can detect clear across the galaxy. These starquakes can continue for weeks at a time. The magnetar sends out aftershocks, each one releasing more energy than our Sun produces in years. The surface gradually settles into a new configuration, slightly different from before. The magnetic field geometry shifts, and then it might stay quiet for years, or decades, or it might crack again tomorrow. We simply cannot predict it. Each magnetar behaves completely differently. Some remain hyperactive, erupting multiple times annually. Others fall silent for decades before suddenly, violently awakening. We're still desperately trying to understand the pattern, because the real mystery runs deeper. Where does a magnetar derive the energy to keep doing this? You cannot see a magnetar's field with human eyes, but it's there, always. A sphere of twisted magnetic energy surrounding the dead star, reaching outward hundreds of miles in every direction. And this field doesn't just attract metallic objects, it destroys reality itself. At 600 miles from a magnetar, the magnetic field strength hits approximately 1 billion Gauss. That's confirmed through spectroscopic measurements of magnetar atmospheres and the cyclotron resonance features visible in their X-ray spectra. At this distance, quantum mechanics itself starts failing. Here's what that actually means in practice. Normally, light travels in perfectly straight lines through empty space, but near a magnetar, light bends. Not because of gravitational forces this time, but purely because of magnetism. The magnetic field achieves such overwhelming strength that it affects the vacuum itself through a phenomenon called vacuum birefringence. Photons traveling through this space split into two separate beams based on their polarization characteristics. Space itself becomes birefringent, like looking through a specialized crystal, but it gets considerably worse for anything containing actual matter. Remember, atoms are held together by electromagnetic forces. Electrons orbit nuclei because of electrical attraction. But a magnetar's magnetic field grows strong enough to completely overwhelm these fundamental forces. The field doesn't just tug gently on electrons, it deforms them. At distances inside 600 miles, atoms elongate into needle-like shapes. The electron clouds that should maintain spherical configurations get stretched along the magnetic field lines like taffy. Chemical bonds cease working the way they should. Molecules cannot form properly. Complex chemistry becomes physically impossible. For any living organism, this represents instant death, not from heat, not from radiation, though there's certainly plenty of that, but from the fundamental breakdown of molecular structure itself. Your cells would stop functioning before you even registered pain. The proteins that run your body would unfold. DNA would unravel. You'd literally come apart at the molecular level. Nothing we've constructed could survive this environment either. Spacecraft hulls would have their atomic bonds disrupted. Electronics would fail instantaneously as the magnetic field induces electrical currents millions of times stronger than their design specifications. Even light itself struggles to escape, bending and splitting as it fights through the distorted space. And this is all assuming you could somehow survive the radiation bombardment, which you absolutely couldn't, because magnetars don't sit quietly inside their magnetic cocoons. They scream. The field isn't static or stable. It shifts, twists, and reconnects constantly, even between major star quakes. Each reconnection event sends out bursts of X-rays and gamma rays. These aren't gentle pulses. They're focused beams of high-energy radiation, powerful enough to ionize anything in their path. But compared to what the field does to space-time itself, even this seems almost routine. Light is supposed to be simple. Photons traveling in straight lines, completely unaffected by magnetic fields. That's what every textbook teaches. That's what works everywhere else throughout the universe. But near a magnetar, this fundamental rule breaks down completely. Scientists first predicted this back in the 1930s, but they assumed it would never matter practically. The effect, called photon splitting and vacuum birefringence, only becomes significant in magnetic fields approaching 10 to the 13th Gauss or higher. No natural object should reach that strength, they thought. Then we found magnetars. Here's what actually happens. In normal space, a true vacuum is genuinely empty. But quantum mechanics reveals that's not quite accurate. Even in a perfect vacuum, virtual particles constantly pop into and out of existence. Electron-positron pairs appear for impossibly brief moments, then annihilate each other. We cannot see this happening directly, but it's real. It's been measured in laboratories through the Casimir effect. Near a magnetar, the magnetic field grows so strong that it polarizes this quantum vacuum. The virtual particles align with the field before they disappear. This alignment fundamentally changes how light travels through space. The vacuum effectively becomes a medium, like air or glass, but made of quantum fluctuations. Light passing through splits into two distinct beams with different polarization characteristics. One beam polarized parallel to the magnetic field, another perpendicular to it. They travel at slightly different speeds. This is vacuum birefringence, and we've confirmed it through observations of magnetar spectra. The light arriving from these objects shows exactly the polarization patterns this theory predicts. But there's another effect even stranger still. At even higher field strengths, above 10 to the 13th Gauss, individual photons can spontaneously split. A single high-energy gamma-ray photon can divide into 2 or 3 lower-energy photons. This isn't science fiction. This is quantum electrodynamics pushed to its absolute theoretical limit. We've observed this indirectly. When magnetars experience major flares, the spectrum of radiation we detect doesn't match what we'd expect from a simple hot surface. There are distinctive features, dips and peaks in the spectrum, that only make sense if photon splitting is actively occurring. The high-energy gamma rays are splitting into lower-energy X-rays before they reach our detectors. This means magnetars are natural laboratories for testing quantum mechanics under conditions we can never recreate on Earth. Our most powerful magnets reach maybe 45 Tesla, approximately 450,000 Gauss. A magnetar's field is roughly 2 billion times stronger than that. It's testing physics in a regime we can only dream of accessing artificially. And yet, this isn't even the most extreme thing magnetars do, because sometimes they don't just bend light, they weaponize it. March 5th, 1979. Every satellite orbiting Earth picked up something impossible. A wave of gamma rays and X-rays slammed into our planet's atmosphere with such overwhelming intensity that it ionized the upper layers. Scientists initially thought it was a nuclear attack. The burst lasted for only 1/5 of a second, but in that instant, it delivered more energy than our Sun produces in 1,000 years. The source was a magnetar in the constellation Norma, approximately 30,000 light-years away, designated SGR 052566. What we witnessed was a massive magnetic flare, the largest ever recorded in human history. This is fully documented. The data came from Soviet Venera spacecraft, American satellites, and observatories worldwide. The event was so powerful that it remains the brightest burst of energy ever detected from beyond our solar system. But here's what makes it truly terrifying. That energy travelled for 30,000 years through empty space. It spread out over an expanding sphere. By the time it reached Earth, it had diluted across an area trillions of miles wide. And it still hit us hard enough to disrupt satellites and alter our ionosphere. Calculate backwards, and the numbers become nightmarish. At the moment of the burst, the magnetar released roughly 10 to the 46th joules of energy. That's more energy than an entire galaxy containing 200 billion stars produces in several years, from a single object 12 miles across, in 1/5 of a second. How is this even remotely possible? The leading theory involves catastrophic magnetic field reorganization. The magnetar's magnetic field, already at impossible strengths, became unstable. Magnetic field lines twisted and tangled over years or decades until they simply couldn't sustain that configuration anymore. Then they snapped. Imagine rubber bands wrapped around a ball, twisted tighter and tighter and tighter. Eventually, they break and whip back violently. But these aren't rubber bands we're talking about. These are magnetic field lines carrying energy equivalent to the mass of small moons, according to Einstein's equation linking mass and energy. When they reconnect, all that energy has to go somewhere. It goes into accelerating particles. Electrons and ions get flung outward at 99% of light speed. These particles slam into the magnetar's own magnetic field further out, creating cascades of gamma rays through a process called synchrotron radiation. The magnetar effectively creates a massive gamma ray cannon firing in all directions simultaneously. For months after the March 1979 event, astronomers detected a pulsing X-ray source at the same location. The magnetar was still vibrating from the violence of the flare, sending out regular pulses every 8 seconds as it rotated. Even after the catastrophic release, it still possessed enough energy to outshine thousands of normal stars. And this raises a disturbing question that keeps scientists awake at night. If magnetars can do this once, can they do it again? Can they do it bigger? Nobody was actively searching for magnetars back then. The word didn't even exist yet in scientific literature. Scientists in the 1970s were still struggling to wrap their heads around neutron stars and pulsars, those rapidly spinning stellar remnants sending out regular radio pulses like cosmic lighthouses. Then on March 5, 1979, the universe decided to introduce us to something far more violent. The gamma ray burst that struck Earth that day didn't fit any existing model. It was too bright, too brief, and too energetic. It came from a fixed point in the sky, not from some distant galaxy. And in the months afterward, that same spot kept pulsing with X-rays every 8 seconds. This wasn't a pulsar behaving normally, this was something else entirely. Scientists called it a soft gamma repeater, or SGR. The name described what they observed, but not what it actually was. It repeated, unlike most gamma ray bursts, and the spectrum was softer, meaning lower energy than typical gamma ray bursts from cosmological distances. But what could possibly cause such behavior? Robert Duncan and Christopher Thompson proposed the answer in 1992. They calculated that a neutron star with a sufficiently powerful magnetic field could store enormous quantities of energy in its twisted magnetic field lines. When those field lines snapped and reconnected, they would release bursts of gamma rays and X-rays. They called these objects magnetars, combining magnetic and star. The theory was highly controversial at first. Some scientists argued that magnetic fields couldn't reach such extreme strengths. Others questioned whether the field could remain stable. But observations kept accumulating. More SGRs were discovered. Their behaviors matched magnetar predictions perfectly. And in 1998, researchers finally measured a magnetic field strength directly. They accomplished this by observing cyclotron resonance features in the X-ray spectrum of a magnetar. When charged particles spiral in a magnetic field, they emit radiation at specific frequencies determined by the field strength. By measuring these frequencies in the X-ray light coming from magnetars, scientists calculated fields of 10 to the 14th to 10 to the 15th Gauss, exactly what Duncan and Thomson had predicted. Since then, we've identified about 30 confirmed magnetars in our galaxy and nearby galaxies. There are probably many more we haven't found yet, either because they're dormant or hidden behind interstellar dust clouds. Each one we study reveals new mysteries. Some are hyperactive, bursting multiple times per year. Others stay silent for decades. Some emit radio waves, others don't. We're still learning the rules, but the discovery taught us something profound. The universe can create objects more extreme than we ever imagined possible. And if magnetars exist, pushing magnetic fields to their theoretical limits, what else might be out there? What other forces might the universe be pushing to their breaking points? August 27th, 1998. The Rossi X-ray Timing Explorer satellite was conducting routine observations of the sky when something extraordinary happened. A magnetar designated SGR 1900 Plime 14 erupted in a massive flare. The burst was so intense that it completely saturated the satellite's detectors, overwhelming them with more X-rays than they were designed to handle. For several hours, the telescope was effectively blind. Its instruments had to reset and recalibrate. Engineers on the ground worried about permanent damage. This wasn't a design flaw. The satellite was specifically built to study X-ray sources, even powerful ones, but nobody anticipated an object that could suddenly become 100,000 times brighter in less than a second. This event wasn't unique either. Multiple X-ray satellites over the years have been temporarily disabled by magnetar flares. In 2004, when SGR 1806-20 had its giant flare, it affected over a dozen spacecraft simultaneously. Swift, Integral, RESI, and others all recorded the burst. Some instruments went into protective shutdown modes. Others had their data corrupted by the sheer intensity of the radiation. Think about what this means for a moment. These satellites orbit Earth approximately 93 million miles from our Sun. They're designed to observe X-ray sources billions of light years away. They have filters, shielding, and safety protocols to handle intense radiation. Yet a magnetar tens of thousands of light years away can still overwhelm them completely. The implications are staggering. If a magnetar flare can blind a satellite across interstellar distances, what would it do up close? The answer is simple and terrifying. Nothing survives. Any spacecraft within several light years of a major magnetar flare would be fried instantly. The radiation would induce currents in every circuit, melting electronics from the inside out. Solar panels would degrade from the particle bombardment. Shielding would be utterly useless against such intensity. But here's the really concerning part that keeps mission planners awake. We have no warning system whatsoever. Magnetars don't announce when they're about to erupt. There's no precursor we can detect. One moment they're relatively quiet, sending out steady X-ray emission. The next moment they explode with energy equivalent to thousands of supernovas compressed into fractions of a second. For future space exploration, This represents a hidden danger we're only beginning to understand. As we send probes deeper into our galaxy, they might encounter magnetars we haven't catalogued yet. A probe could be cruising through interstellar space, completely unaware that a dormant magnetar lies just a few light years away. Then, without warning, that magnetar wakes up. The probe would die before its sensors even registered what happened. Scientists are now working on better detection methods. They want to map every magnetar in our galaxy and monitor them constantly. Early warning could potentially save missions, but there's a fundamental problem. Dormant magnetars are almost invisible. They emit so little radiation that we can barely detect them even with our best instruments. We might have dozens or even hundreds lurking in our galaxy right now, completely unknown to us. And each one is a loaded weapon waiting to fire. Our galaxy contains roughly 200 billion stars. About 1 billion of those will eventually explode as supernovas. Many will leave behind neutron stars. Scientists estimate there might be 100 million neutron stars scattered throughout the Milky Way. Yet we've only confirmed about 30 magnetars. What makes them so incredibly rare? The answer starts with how they're born. Not every neutron star becomes a magnetar. The original star needs very specific conditions. It must be massive enough to produce a neutron star, but not so massive that it collapses into a black hole. That's a narrow range, roughly 8 to 20 times our Sun's mass. But mass alone isn't enough. The star also needs to be spinning rapidly when it collapses. As the core compresses, conservation of angular momentum makes it spin faster and faster. This spinning, combined with the convective motions in the collapsing material, creates a dynamo effect. This dynamo amplifies the magnetic field to extreme levels. Think of it like a cosmic generator. The collapse itself generates the initial energy. The spinning motion organizes that energy into a coherent magnetic field. But this only works if conditions are precisely right. The rotation speed, the mass distribution, the initial magnetic field strength, all these factors have to align perfectly. It's exceptionally rare. Even when a magnetar does form, it doesn't stay that way forever. The extreme magnetic field gradually decays over time. Scientists estimate that magnetars remain active for only about 10,000 years, maybe less. After that, the field weakens to normal neutron star levels. The object settles down, becoming an ordinary pulsar or simply a quiet neutron star. This short active lifetime explains why we see so few at any given time. At any moment, only a tiny fraction of neutron stars are in their magnetar phase. The rest have either not yet become magnetars or have already passed through that phase. It's a brief, violent stage in a neutron star's long existence. But there's another reason our count stays low. Detection. Magnetars are small, about 12 miles across. They're incredibly distant, often tens of thousands of light years away. And unless they're actively flaring, they're dim compared to other astronomical objects. Many might be dormant right now, invisible to our telescopes, waiting for their next outburst. We only find magnetars when they do something dramatic. A major flare lights them up across the electromagnetic spectrum. Then we can study them, measure their properties, confirm they're magnetars. But a quiet magnetar could be lurking nearby, and we'd never know. In fact, scientists suspect there might be many more magnetars than we've confirmed, perhaps hundreds in our galaxy alone. Most are dormant, their surfaces cooling, their magnetic fields slowly decaying. They'll flare again eventually, years, decades, or centuries from now, but until then, they remain hidden in the darkness. Which means there might be one closer than we think. Distance usually means safety in space. A supernova, 10,000 light-years away, is spectacular but harmless. Even a gamma-ray burst, if it's not pointed directly at us, poses no threat from such distances. But magnetars completely change the calculation. Scientists have run the numbers, and they're deeply disturbing. If a magnetar within 10 light-years of Earth experienced a giant flare, one comparable to the December 2004 event, the radiation would be absolutely devastating. The burst would hit our atmosphere with enough energy to partially destroy the ozone layer. UV radiation from our sun would spike dramatically. Extinction events would follow. But here's what keeps astronomers up at night. 10 light-years is close. Very close. There are only about a dozen stars within that radius. The odds of a magnetar being that close are extremely low. But at 10,000 light-years, there are millions of stars at that distance. And we know magnetars exist in that range. We've detected them. A hyperflare from 10,000 light-years away wouldn't destroy our ozone layer, but it would cause noticeable effects. The ionosphere would light up, satellites would be damaged, radio communications could fail, and if the flare was strong enough, if it reached the extreme end of what magnetars are theoretically capable of, even from that distance, it might cause biological harm. The worst-case scenario involves a magnetar hyperflare pointed directly at Earth. Remember, magnetars emit focused beams of radiation from their magnetic poles. As they rotate, these beams sweep across space like lighthouse beams. If Earth happened to be in the direct path during a giant flare, we'd receive the full intensity, not just scattered radiation. From 10,000 light-years, such a beam could deliver radiation doses comparable to being near a nuclear explosion. Not everywhere on Earth, just the side facing the magnetar at that moment. But that would be enough. Power grids would fail from the electromagnetic pulse. Electronics would fry, and living tissue would absorb dangerous levels of gamma rays and X-rays. Scientists estimate that a magnetar hyperflare from this distance could increase cancer rates worldwide for decades. Afterward, it wouldn't be an immediate extinction event, but it would be a catastrophe. And there's no way to prepare, no warning system, no defense. The geological record might already contain evidence of past magnetar flares. Some mass extinctions have no clear cause. Researchers have looked for signs of increased radiation exposure in the fossil record. Certain layers show mutations and cellular damage consistent with radiation exposure, but the source remains unknown. Could a magnetar have fired at Earth millions of years ago? We can't prove it yet, but the possibility exists. And it's chilling, because somewhere out there right now, a magnetar might be building up stress in its crust. In years or decades, it will crack. Its magnetic field will unleash a beam of death into the galaxy. And all we can do is hope we're not in the way. Imagine standing on a magnetar's surface. You can't, because you'd be dead instantly. But imagine it anyway. Under your feet, if you had feet, would be a landscape that defies everything we know about solid matter. The crust is iron, pure iron, compressed to densities millions of times greater than steel. It's arranged in a crystalline structure so perfect that it makes diamonds look disordered. This is the hardest substance in the universe. Nothing we can create in laboratories comes even remotely close. Scientists have tried to simulate these conditions and failed completely. The pressures and densities are simply beyond our technological reach. But this iron isn't static or stable. The intense magnetic field threads through it, creating currents and eddies of electric charge. These currents generate heat, not the kind of heat you feel from a fire. We're talking millions of degrees. The surface temperature of a young magnetar can reach 10 million degrees. That's hotter than the core of our sun. At these temperatures, even crystalline iron starts to behave strangely. The outer layers, just the top few yards, exist in a state between solid and liquid. The atoms vibrate so violently that they can slip past each other, like metal that's almost melting but held in place by the crushing gravity. Deeper down, the pressure increases and the material stays solid. But the surface has this weird plasticity. When a starquake happens, this iron crust cracks, but not like glass shattering. The crack moves at a significant fraction of light speed, propagating through the ultra-dense material faster than sound travels through normal matter. The two sides of the crack suddenly shift, creating a shear motion that releases the stored magnetic energy. The surface ripples. Waves move through the solid iron like water ripples in a pond. Except these ripples are moving through material billions of times denser than water. The magnetar rings like a bell, oscillating at specific frequencies determined by its size, mass, and internal structure. These oscillations continue for weeks or months, gradually damping down as the energy dissipates. But the surface doesn't just crack and ring, it also erupts. The magnetic energy release heats material to billions of degrees in microseconds. Iron vaporizes despite the intense gravity trying to hold it down. A plume of ionized iron plasma, an atmosphere suddenly created by violence, rises above the surface. This atmosphere is temporary, lasting maybe seconds or minutes before gravity pulls it back down. During those brief moments, the magnetar has a real atmosphere, thin but detectable. Spectroscopic observations have actually captured this phenomenon. When magnetars flare, their spectra show absorption lines from iron, silicon, and other elements. These lines tell us what the surface is made of and how hot it is. The data confirms our models. The surface is indeed iron, and it's indeed unimaginably hot. Beneath the crust lies something even stranger, a liquid layer of neutrons, unbound from protons, flowing freely. Scientists call this a neutron superfluid because it flows without any friction or viscosity whatsoever. Deeper still, the neutrons might form exotic states of matter that we can barely describe with current physics. But all of that is hidden beneath the iron, and the iron itself is already beyond our comprehension. Most magnetars don't have atmospheres, not like Earth's atmosphere anyway. The gravity is so intense that any gas would be pulled down and crushed into the surface almost instantly. But magnetars do have something, a layer so thin it's barely there, yet so heavy it defies belief. Scientists call it a photosphere, though that's not quite accurate. It's the region where photons can finally escape from the dense material below. In normal stars, the photosphere is thousands of miles thick. In a magnetar, it's measured in centimeters, sometimes less. A layer just one atom thick, but that layer weighs millions of tons per square inch. The density is so high that a single cubic centimeter contains more mass than a mountain. The photons struggling to escape through this layer get scattered billions of times, bouncing between atoms and electrons before finally breaking free. This scattering alters the spectrum we observe, creating the unique fingerprints that identify magnetars. The magnetic field plays a crucial role here too. It's so strong that it confines any material trying to escape. Electrons, ions, everything gets trapped along magnetic field lines. They can move along these lines but not across them. The result is a highly structured atmosphere, more like columns and sheets than a uniform gas layer. When a magnetar flares, the magnetic field lines above the surface reconnect. This magnetic reconnection suddenly releases trapped material. Plasma that was held in magnetic loops gets flung outward at high speeds. For a brief time, the magnetar develops a real atmosphere, extending maybe 100 miles above the surface. This ejected material cools as it expands, emitting X-rays and gamma rays. We can observe this emission with our telescopes. The spectrum shows features that reveal the temperature, density, and magnetic field strength of the material. It's one of the few ways we can probe conditions near a magnetar's surface. But gravity always wins in the end. The escaped material doesn't have enough velocity to reach escape velocity. It arcs back down, crashing into the surface at speeds of thousands of miles per second. The impact creates more X-rays, more heat, and sometimes triggers additional magnetic activity. The whole event can last hours or days. Between flares, the atmosphere essentially disappears. Individual atoms might hover temporarily before falling back. Particles trapped in magnetic field lines spiral endlessly, but there's no continuous gaseous layer, no weather, no atmospheric circulation, just crushing gravity, searing radiation, and magnetic field lines so twisted they form cages of pure force. This is as close to a naked stellar core as nature allows. The surface of a magnetar is matter at its absolute limit, physics at its breaking point, and yet somehow it's stable. It exists. A 12-mile sphere of impossibility floating in the dark, waiting to remind us that the universe still has secrets we can't fully explain. Einstein taught us that gravity warps space-time. The stronger the gravity, the more time slows down relative to an outside observer. We've tested this with atomic clocks on airplanes and satellites. The effect is real and measurable. But near a magnetar, time doesn't just slow down, it nearly stops. Calculate the gravitational time dilation at a magnetar's surface, and you get numbers that seem impossible. For every second that passes on the magnetar, roughly 1.3 seconds pass for someone far away. That's a 30% difference. If you somehow stood on a magnetar for 1 year, about 16 months would pass for the rest of the universe. This isn't speculation. The math is straightforward general relativity. We can measure it indirectly through the light coming from magnetars. Photons climbing out of the intense gravitational field lose energy. They get redshifted, their wavelengths stretched. The amount of redshift tells us exactly how strong the gravity is, and the calculations match theoretical predictions perfectly. But time dilation creates strange situations. Imagine watching a magnetar from a distance with a perfect telescope. You see its surface. A star quake happens. From your perspective, the crack spreads across the surface more slowly than it would if you were right there. The oscillations that follow appear stretched out in time. The entire event looks like it's happening in slow motion. Meanwhile, if you were somehow on the surface experiencing it, time would feel completely normal to you. The crack would spread at its true speed. The oscillations would ring at their natural frequency. You wouldn't notice anything strange about time itself. It's only when you compare your clock to a distant observer's clock that the difference appears. This has real consequences for the physics happening on the magnetar. Nuclear reactions, particle decays, all processes that depend on time run at different rates depending on where you measure them. A neutron near the surface would decay more slowly from an outside perspective than a neutron far from the magnetar. The difference is measurable and significant. Scientists use these time dilation effects to test general relativity in extreme conditions. Magnetars provide a natural laboratory where gravity is strong enough to create noticeable effects, but not so strong that everything collapses into a black hole. They're right at the edge, the perfect testing ground. Some researchers have proposed that magnetars could be used for precision tests of alternative gravity theories. If general relativity breaks down anywhere, it would be here, where space-time is stretched to its limit. So far, the observations match Einstein's predictions exactly, but we keep watching, keep measuring, hoping to find a crack in the theory, because if general relativity does fail near magnetars, it would revolutionize physics. We'd need entirely new theories to explain what holds these objects together, how they behave, why they don't collapse. The implications would ripple through every branch of science. But for now, Einstein still reigns supreme. Time bends near Magnetars exactly as he predicted a century ago, and that bending is yet another way these objects warp reality itself. Here's a problem that keeps physicists awake at night. Magnetic fields decay. Always. Every magnet you've ever held will eventually lose its magnetism. The atoms that create the field slowly drift out of alignment. Energy dissipates as heat. It's inevitable. So why don't magnetar fields decay faster? They do decay, actually, but incredibly slowly. Scientists estimate a magnetar's field has a half-life of about 10,000 years. That means after 10,000 years, the field strength drops by half. After another 10,000 years, it halves again. Given enough time, a magnetar should become an ordinary neutron star with a much weaker field. But here's the mystery that nobody can solve. The energy stored in a magnetar's magnetic field is enormous. We're talking about 10 to the 47th joules. That's roughly the mass energy equivalent of a small planet, according to Einstein's famous equation. That energy has to come from somewhere, and it has to be maintained somehow, at least for a while. The leading theory involves the magnetar's rotation. When a magnetar forms, it's spinning incredibly fast, maybe 1,000 times per second. This rotation, combined with convective motions in the newly formed neutron star, could generate the initial magnetic field through a dynamo process. It's similar to how Earth generates its magnetic field, but cranked up to impossible extremes. But there's a catch. For this to work, the magnetar needs a power source to drive the dynamo. Rotation provides some energy, but not enough. Scientists think the key might lie in the magnetar's internal structure. Neutron stars aren't uniform spheres. They have layers, crusts, superfluid cores. Different layers might rotate at different speeds, creating shear forces. These forces could maintain the magnetic field through continued dynamo action. Another possibility involves exotic matter. In the core of a neutron star, pressures are so extreme that neutrons might break down into their constituent quarks. These quarks could form strange states of matter, like quark-gluon plasma, or even stranger configurations. Some theories suggest that these exotic states have unique magnetic properties that could sustain ultra-strong fields indefinitely. We don't know which theory is correct. Maybe all of them contribute. Maybe there's another mechanism we haven't thought of yet. The data we have isn't detailed enough to rule out options definitively. We need more observations, better models, and perhaps entirely new physics to fully understand how magnetars maintain their fields. But here's what we do know with certainty. The field is there, it's measured, it's confirmed, and it's doing things that shouldn't be possible according to our standard models of magnetic field decay. Magnetars are violating expectations, pushing beyond what we thought nature allowed. And every observation raises new questions instead of providing answers. Some magnetars seem to have fields that are increasing rather than decreasing. How is that even possible? Others show complex field geometries that don't match simple dipole models. The field isn't just strong, it's structured, twisted, knotted in ways we're only beginning to map. These objects are telling us that we don't understand magnetic fields as well as we thought. Not at extreme energies, not in extreme conditions. And until we crack this mystery, magnetars will remain one step ahead of our theories. Not all magnetars behave the same way. Some are hyperactive, erupting dozens of times per year. Others go silent for decades, only to suddenly wake up with a massive flare. This inconsistency has puzzled scientists since we first discovered these objects. What determines a magnetar's behavior? SGR 1806-20 was dormant for over 20 years, quiet, unassuming. Then on December 27, 2004, it produced the largest burst ever recorded. The entire astronomical community was stunned. What triggered it? Why then? We still don't have complete answers. Compare that to SGR 1900 plus 14, one of the most active magnetars known. Between 1998 and 2002, it erupted hundreds of times. Some bursts were small, others were major events. Then it calmed down. Now it's relatively quiet, only producing occasional bursts. What changed? Scientists have proposed several theories. One involves the magnetar's age. Young magnetars, recently formed, might be more active because their crusts are still settling. The magnetic field is still reorganizing, causing frequent starquakes and flares. As the magnetar ages, it stabilizes. Activity decreases. This matches some observations, but not all. Another theory focuses on magnetic field geometry. If the field is highly twisted and complex, it might store more energy and lead to more frequent reconnection events. Simpler field geometries might be more stable, but we can't directly observe a magnetar's field structure. We have to infer it from the timing and spectrum of bursts, which leaves enormous uncertainty. Temperature might also play a role. Magnetars cool over time as they radiate away their internal heat. A hotter magnetar might have a more fluid interior, allowing the crust and core to interact more dynamically. This could trigger more starquakes. As the magnetar cools, the interior stiffens. Activity drops. This theory has some support from thermal emission observations, but none of these theories fully explain the data. Some magnetars don't follow the expected patterns. They stay active longer than they should, or they go quiet earlier than predicted. And the sudden awakening of dormant magnetars, like the 2004 event, suggests that even a seemingly dead magnetar can harbour hidden stresses ready to erupt without warning. There might also be external factors we haven't considered. Could interactions with nearby objects trigger flares? If a magnetar is in a binary system, maybe the companion star's gravitational influence causes tidal stresses that eventually lead to starquakes. Most known magnetars appear to be isolated, but we might have missed companions in some cases. Or perhaps it's purely random. The stresses build up chaotically, and when the crust finally cracks depends on countless tiny factors we can't measure or predict. Like earthquakes on Earth, magnetar flares might be fundamentally unpredictable beyond statistical probabilities. This unpredictability is both fascinating and frustrating. It means every magnetar is a unique case study. It also means we can't forecast when the next major flare will happen. All we can do is watch, wait, and hope our telescopes are pointed in the right direction when it occurs. Gamma-ray bursts are the brightest events in the universe. For a few seconds, a gamma-ray burst can outshine every other object in the observable cosmos combined. Astronomers have detected these bursts from galaxies billions of light-years away, so distant that the light has travelled for most of the universe's history, and magnetars might be creating some of them. Most gamma-ray bursts come from two sources we've identified. Long-duration bursts, lasting more than 2 seconds, come from massive stars collapsing into black holes. Short-duration bursts, under 2 seconds, come from neutron star collisions. But there's a third category that doesn't fit either model. Some bursts are too short to be collapsing stars, too bright to be ordinary neutron star mergers, and their spectra show features that match magnetar flares. In 2004, when SGR 1806-20 had its giant flare, it was briefly visible from the Andromeda Galaxy, 2.5 million light-years away. If that same event had occurred in a distant galaxy, say 10 billion light-years away, we would have detected it as a short gamma-ray burst. We might have classified it as a neutron star merger or some other event, never guessing it was actually a magnetar. This realization changed how we interpret gamma-ray bursts entirely. Some bursts we've been attributing to other causes might actually be magnetar giant flares from distant galaxies. If true, it means magnetars are even more common than we thought. Every galaxy might host dozens or hundreds of these objects, occasionally producing bursts we can detect across cosmic distances. But there's an even more intriguing connection. Some scientists think magnetars might power certain types of supernovas. Not the supernova that creates the magnetar, but later events. Here's how it could work. A young magnetar, spinning incredibly fast, could inject energy into the expanding debris of its parent supernova. This energy would make the supernova appear much brighter and last much longer than normal. We've observed supernovas that don't match standard models. They're too bright, or they fade too slowly. Researchers call these superluminous supernovas. Some have spectra consistent with magnetar-powered emission. The magnetar's spin-down energy, as it gradually slows due to magnetic braking, gets converted into radiation that lights up the surrounding gas. It's like having a cosmic light bulb inside the supernova remnant, continuously pumping energy into the expanding shell. If this is correct, magnetars aren't just interesting in their own right. They're key players in multiple cosmic phenomena. They shape supernova evolution. They create gamma-ray bursts. They might even seed the universe with heavy elements through their violent eruptions. The material they blast into space, enriched with iron and other metals, could contribute to the chemical makeup of future generations of stars and planets. This web of connections shows how important magnetars are to cosmic ecology. They're not isolated oddities existing in a vacuum. They're part of the grand cycle of stellar birth, life, and death. And every time we study one, we learn something new about how the universe works on the largest scales. Imagine this scenario carefully. A massive star roughly 200 light-years from our solar system reaches the end of its life. It explodes in a supernova. We see the spectacular light show. Beautiful, harmless at that distance. But the core collapses into a magnetar. What happens next? Initially, nothing concerning. 200 light-years is far enough that even a magnetar poses no immediate threat. Its magnetic field, while intense, drops off rapidly with distance. At 200 light-years, the field strength would be negligible. We wouldn't detect anything unusual beyond the supernova itself. But magnetars don't stay quiet. Within years or decades, it would experience its first major flare. Let's say it produces a burst comparable to the December 2004 event. The radiation would travel toward Earth at light speed. 200 years later, it would arrive. The burst would light up our night sky. Not as bright as the full moon, but noticeable. A point of light suddenly appearing, brighter than any star. It would last less than a second, then fade. Astronomers would scramble to figure out what they just witnessed. Telescopes would focus on the location, and they would find the magnetar still pulsing, still sending out X-rays. But here's the concerning part. The radiation dose Earth receives from 200 light-years would be minor. Background radiation levels would spike slightly. Satellites might experience minor glitches. But nothing catastrophic. Now imagine the magnetar is only 20 light-years away. At 20 light-years, a giant flare would be genuinely dangerous. The X-ray and gamma-ray dose would penetrate our atmosphere significantly. The ozone layer would take damage. Not complete destruction, but enough to increase surface UV radiation for years afterward. Cancer rates would climb. Ecosystems sensitive to UV radiation would struggle. Marine plankton, which form the base of the ocean food chain, would die off in large numbers. At 10 light-years, we're in catastrophe territory. A magnetar giant flare from this distance would be an extinction-level event. The ozone layer would be shredded. UV radiation from our sun would sterilize the surface. complex life would retreat to caves and deep oceans. Some species would survive, but most wouldn't. Human civilization would face complete collapse. And here's the truly terrifying thought that keeps astrobiologists awake. We wouldn't know until it was over. The flare travels at light speed. There's no warning, no advance notice. One moment, everything is normal. The next, our sky lights up with deadly radiation. By the time we detect it, we're already bathed in it. There's no time to prepare, no chance to protect ourselves. Fortunately, the odds are extremely low. Massive stars capable of producing magnetars are rare. Most are far away. The nearest known massive star is probably over 100 light-years away. And even if it did go supernova, the chance of the core becoming a magnetar rather than a black hole or regular neutron star is maybe 1 in 10. And then the chance of it flaring toward Earth during its brief active lifetime is even smaller. But the universe is old and large. Somewhere, sometime, a civilization might not be so lucky. They might live near a magnetar, and when it wakes up, their story ends. No warning, no escape, just sudden, violent extinction. Black holes get all the attention. They're the universe's ultimate destroyers. The objects that swallow everything. Nothing escapes, not even light. Pop culture loves them. Movies feature them as cosmic villains. But ask a physicist which object is actually more dangerous, and you might get a surprising answer. Magnetars. Here's the argument. Black holes destroy through gravity. Get too close, past the event horizon, and you're gone. Erased from existence. But the event horizon is small. For a stellar mass black hole, maybe 60 miles across. Stay outside that radius and you're relatively safe. Yes, there's radiation from the accretion disk if the black hole is feeding. But a dormant black hole, one not actively consuming matter, is essentially invisible and harmless unless you fly directly into it. Magnetars kill at a distance. Their magnetic fields extend thousands of miles. Their radiation bursts travel across light years. They don't need to be close to cause damage. A magnetar could be sitting 10 light years away, and if it flares in your direction, you're dead. A black hole 10 light years away is just another dark object in space, posing no threat whatsoever. The destructive range is completely different. Scientists have calculated the danger zones precisely. For a black hole, the lethal radius is measured in thousands of miles at most. You have to be practically touching it for gravity to tear you apart. For a magnetar, the lethal radius extends to potentially dozens of light years when accounting for giant flares. That's billions of times larger. But black hole advocates push back. They argue that black holes are forever. A magnetar is active for maybe 10,000 years. A black hole exists until the universe ends, slowly evaporating through Hawking radiation over timescales measured in googles of years. Given enough time, a black hole will consume more matter, destroy more structure, and have a greater cumulative impact on the universe. They also point to supermassive black holes at galaxy centers. These monsters contain billions of times the mass of our Sun. When they're actively feeding, they create jets of radiation and matter that extend hundreds of thousands of light years. These jets sterilize entire regions of galaxies, preventing star formation and wiping out any life that might have emerged. No magnetar can compete with that scale of destruction. Yet the magnetar supporters have a compelling counter-argument. Those supermassive black holes cause gradual destruction over millions of years. A magnetar flare is instant, civilization ending in less than a second. There's something uniquely terrifying about that immediacy. Black holes give you time. You can see them coming, detect their gravitational effects, avoid them. Magnetars don't give you that luxury. There's also the question of which is more violent relative to size. A magnetar just 12 miles across can release more energy in a fraction of a second than thousands of stars produce in years. A stellar mass black hole, even when feeding actively, can't match that energy output. Pound for pound, magnetars win decisively. The debate remains unresolved in the scientific community. Both objects represent physics at its most extreme. Both can end worlds without mercy, but they do it differently. Black holes erase through gravity, slowly, inevitably, like a cosmic drain pulling everything toward oblivion. Magnetars attack with radiation and magnetism, suddenly, explosively, like cosmic bombs that can detonate without warning. Maybe the real answer is that we should fear both equally. The universe has created multiple ways to destroy life, and arguing about which is worse seems pointless when either one near Earth would mean the end of everything we know and love. Every atom in your body except hydrogen came from stars. This isn't poetry or metaphor, it's confirmed science. Carbon, oxygen, nitrogen, iron, all these elements were forged in stellar cores and scattered into space when stars died. But there's a mystery in the data. Some heavy elements, the really massive ones, shouldn't exist in the quantities we observe throughout the universe. Creating elements heavier than iron requires very specific conditions. You need intense neutron bombardment, temperatures in the billions of degrees, and precise timing. Supernovas provide some of this. Neutron star collisions provide more. But calculations show these sources alone can't explain all the heavy elements we detect in the universe. Something else must be contributing. Enter magnetars. When a magnetar erupts, it doesn't just release radiation, it ejects matter. Neutron-rich material from the surface gets blasted into space at significant fractions of light speed. This material is incredibly dense, packed with neutrons that haven't yet decayed. And it's moving through a radiation field intense enough to drive nuclear reactions. These conditions are perfect for rapid neutron capture, the R process that creates heavy elements. Neutrons slam into existing nuclei, building heavier and heavier atoms in milliseconds. Gold, platinum, uranium, elements that are rare and precious on Earth, form in abundance during these violent events. The magnetar is essentially a cosmic foundry, manufacturing heavy elements through pure violence. Scientists have found evidence supporting this in meteorite samples. Some ancient meteorites contain isotope ratios that don't match supernova predictions. They show excess amounts of certain heavy elements, enriched beyond what standard models produce. The ratios match what you'd expect from R-process nucleosynthesis in extreme magnetic fields. The implications are staggering. Every gold atom in existence might have passed through a magnetar flare billions of years ago. The platinum in catalytic converters, the uranium in nuclear reactors, the rare earth elements in your smartphone, all possibly created during moments of unimaginable violence on magnetar surfaces long before Earth even existed. But there's more to the story. The ejected material doesn't just float off harmlessly into space. It slams into the surrounding gas and dust at high velocity, creating powerful shock waves. These shock waves compress the material, triggering star formation. New stars born from magnetar ejecta would be enriched with heavy elements from the start. Their planets would have more metal, more complex chemistry, better conditions for life to emerge and thrive. This creates a feedback loop. Magnetars create heavy elements. Those elements form new stars and planets. Some of those stars eventually become magnetars themselves. The cycle continues, gradually enriching the universe with heavier and heavier elements over cosmic time. Over billions of years, this process transforms the chemical composition of entire galaxies. We might owe our existence to magnetars. Earth's iron core, the metals in our technology, even the trace elements essential for biology, like zinc, copper, and iodine, might have originated in magnetar flares billions of years ago. Without these violent events, our planet might have been too metal-poor to develop complex life. So the next time you hold a piece of gold jewelry or use a device with rare earth elements, remember something profound. That matter survived the most extreme conditions in the universe. It was born in magnetic fields that warp reality, ejected in flares that outshine galaxies, and scattered across space to eventually become part of your world. The universe creates through destruction, and magnetars are its most efficient creators. In 2007, astronomers detected something completely unexpected and utterly baffling. A brief radio pulse lasting just 5 milliseconds, coming from billions of light-years away. The burst contained as much energy as our sun produces in an entire day, compressed into a time span shorter than a heartbeat. They called it a fast radio burst, and nobody knew what caused it. At first, scientists thought it was an error, radio interference from Earth-based sources, satellite glitches, anything but an actual cosmic signal. But more bursts appeared. Different telescopes, different locations, all detecting similar pulses. By 2020, astronomers had catalogued over 1,000 fast radio bursts. They were real, they were common, and they were mysterious. Here's what made them so strange. The bursts came from random directions across the sky. They didn't repeat, at least most of them didn't. They showed no pattern. The energy required to produce them was enormous. Yet the source had to be incredibly small to pulse that quickly. Only a compact object could flicker in milliseconds. That meant neutron stars or black holes. But doing what? Some fast radio bursts did repeat. The same spot in the sky would pulse again days or months later. This was crucial. It meant the source wasn't destroying itself. Whatever created these bursts survived to burst again. That ruled out catastrophic events like supernova explosions or neutron star collisions. Then in 2020 came the breakthrough that changed everything. A fast radio burst was detected from within our own galaxy. The location matched a known magnetar, SGR 1935 +2 2154. The timing matched a period when the magnetar was actively flaring. The connection was undeniable. At least some fast radio bursts come from magnetars. But how? Magnetars emit X-rays and gamma rays during flares. Radio waves are completely different, much lower energy. Creating intense radio emission requires specific conditions. Charged particles need to be accelerated in magnetic fields, then made to emit coherent radiation. It's a complex process that scientists are still working to understand fully. The leading theory involves magnetic field line reconnection outside the magnetar. When field lines snap and reconfigure, they create electric fields that accelerate electrons to extreme speeds. These electrons, moving through the intense magnetic field, emit synchrotron radiation. Under the right conditions, this radiation becomes coherent, amplifying into a powerful radio pulse that beams out into space. Not all scientists accept this explanation yet. Some argue that magnetars can't produce the brightest fast radio bursts we've detected. Those require even more extreme conditions. They propose alternatives involving binary systems, strange quark matter, or even more exotic physics. The debate continues actively. What we do know is that fast radio bursts are now a powerful tool for studying the universe. The radio waves travel through intergalactic space, getting dispersed by free electrons along the way. By measuring this dispersion, we can calculate how much matter the signal passed through. This tells us about the distribution of material between galaxies, the stuff we normally can't see. Fast radio bursts have also revealed that the universe is more crowded than we thought. If magnetars are producing these signals, and we're detecting thousands of them from distant galaxies, then magnetars must be incredibly common. Every galaxy might host hundreds or thousands. We're only seeing the tip of a vast population. And here's the unsettling part that keeps cosmologists thinking. Some fast radio bursts are coming from objects billions of light years away. The signals left those sources when the universe was young. We're detecting echoes of magnetar violence from cosmic dawn. And if magnetars existed back then, they might have shaped the early universe in ways we're only beginning to understand. Inside every magnetar is a mystery we may never fully solve. We know the outer crust is crystalline iron. We know there's a neutron superfluid layer beneath. But the core, the very center where pressure reaches its absolute maximum, that's where things get truly strange. And some physicists think the core might contain matter that doesn't exist anywhere else in the universe. At the center of a magnetar, the pressure reaches 1 to 2 times 10 to the 35th pascals. That's a number so large it's meaningless in everyday terms. It's billions of times higher than the pressure at the Earth's core. At these extremes, neutrons themselves might break down into their constituent quarks. This creates quark matter, a state so dense that the boundaries between individual particles blur completely. Quarks normally exist in groups of 3, forming protons and neutrons. But under extreme pressure, these groups might dissolve entirely. The quarks would flow freely, creating a quark-gluon plasma similar to what existed microseconds after the Big Bang. Laboratory experiments at particle colliders have created tiny amounts of this material, existing for mere moments before decaying. Inside magnetars, it could be stable and permanent. But there's an even stranger possibility that borders on science fiction. Strange quark matter. Quarks come in 6 types called flavors. Up and down quarks form normal matter. But there are also strange quarks, charm quarks, top and bottom quarks. Under normal conditions, these exotic quarks are unstable and decay quickly. But at magnetar core pressures, strange quarks might become stable. If this happens, the core could transform into strange quark matter, a material theorized but never confirmed to exist. This substance would be denser than normal neutron matter and potentially more stable. Some calculations suggest that strange quark matter might actually be the true ground state of matter, meaning regular atoms are just metastable configurations waiting to convert. This leads to a terrifying scenario. If strange quark matter is more stable, contact with normal matter could trigger a chain reaction. The normal matter converts to strange matter on contact. This conversion releases energy, triggering more conversions. In theory, a single speck of strange matter could convert an entire planet in minutes. Scientists call these hypothetical objects strange stars or quark stars. From the outside, they'd look similar to neutron stars. Same size, similar mass, similar surface gravity, but the interior would be fundamentally different, and some researchers think magnetars might actually be quark stars rather than neutron stars. The extreme magnetic fields could be a signature of the exotic matter inside. There's limited evidence supporting this. Some magnetar observations show properties that don't quite match pure neutron star models. Their masses, radii, and cooling rates sometimes deviate slightly from predictions. These deviations could indicate an exotic composition, but the data isn't conclusive. Regular neutron stars with unusual internal structure might also explain the observations. Testing this requires better measurements. We need to precisely determine magnetar masses and radii. We need to observe their cooling behavior over decades, and we need to detect their gravitational waves if they produce any. These measurements could reveal whether the cores are made of neutrons or something stranger. The implications extend far beyond magnetars. If quark matter exists stably in nature, It changes our understanding of matter itself. It means the periodic table isn't the end of the story. There are denser, more compact arrangements of quarks waiting to be discovered. And somewhere in the universe, in the cores of the densest objects we know, that matter exists right now. We might be living in a universe where most matter is in an excited state, kept from its true form only by the absence of extreme pressure. Magnetar cores could be windows into the fundamental nature of reality, showing us what matter really is when gravity strips away all pretense. February 18th, 2008. The European Space Agency's Integral satellite was conducting a routine gamma-ray survey. Its instruments were calibrated perfectly, its systems nominal. Then, without warning, every detector went blind. The satellite's data stream filled with noise. Engineers on the ground scrambled to understand what happened. The culprit was SGR 0501-6, a magnetar about 16,000 light-years away. It had erupted in a massive flare, sending a wave of gamma rays and X-rays across the galaxy. The burst lasted only seconds, but in that time it delivered more high-energy radiation to Integral than the satellite normally received in months. Integral wasn't designed for this. Its instruments could handle typical gamma-ray sources, even powerful ones. But a magnetar flare at close range, cosmically speaking, overwhelmed every safety margin. The detectors saturated. Electronics experienced massive induced currents from the electromagnetic pulse. For several minutes, the satellite was effectively useless. But here's the remarkable part. Integral survived. Its systems rebooted automatically. Detectors reset themselves. Within an hour, the satellite was back online, slightly damaged, but functional. It had been hit by radiation equivalent to a point-blank nuclear explosion, and it kept working. That's engineering excellence combined with incredible luck. The luck was in the orientation. When the burst arrived, Integral happened to be positioned so its main instruments were pointing away from the magnetar. The radiation hit the side of the spacecraft, not the sensitive detector faces. If the satellite had been oriented differently, the instruments would have taken the full blast directly. They probably wouldn't have survived. Other spacecraft weren't so fortunate. The Swift satellite, designed specifically to detect gamma-ray bursts, was also observing when the flare hit. Its instruments saturated even more completely than Integral's. It took hours to fully recover. Some detectors showed permanent damage, slightly degraded performance that persisted for the rest of the mission. The Mars Odyssey orbiter, circling Mars at the time, detected the burst as well. It wasn't even designed to observe gamma rays. But the flare was so intense that its radiation sensors, meant to measure particle flux near Mars, went off scale. For a moment, Mars Odyssey thought it was being bombarded by a solar storm. Only later did scientists realize the radiation came from across the galaxy. This event taught spacecraft designers a hard lesson. The universe contains hazards they hadn't fully accounted for. Magnetar flares are rare, but they're catastrophic when they occur. Future deep space missions need shielding and protection against sudden radiation surges that might come from any direction without warning. NASA and other space agencies now factor magnetar flares into their risk assessments. For missions to the outer solar system, missions that will be operational for decades, the probability of encountering at least one major magnetar flare is significant. Engineers are designing more robust electronics, better shielding, and automated protection systems that can respond in milliseconds. But there's only so much you can do. A truly giant flare, one comparable to the March 1979 event, would destroy most spacecraft regardless of shielding. The radiation intensity would simply be too high. Electronics would fry. Solar panels would degrade instantly. Even the spacecraft structure itself might suffer damage from the intense electromagnetic fields, inducing currents through metal components. Future interstellar probes face even greater risks. As we send spacecraft toward nearby stars, they'll spend decades or centuries in deep space. The probability of a magnetar flare intersecting their path increases with time. We might lose probes to events we can't predict or prevent. It's a sobering thought. Our ambitions to explore the galaxy are constrained by the galaxy's own violence. Every magnetar will die eventually, not in the explosive sense, but in the slow decline of energy. The magnetic field will weaken, the rotation will slow, the surface will cool. Eventually, the object that once terrorized its corner of space will become quiet, dormant, almost invisible. But what happens then? Scientists have debated this for decades. The answer depends on mass. A magnetar's mass determines its ultimate fate, just as mass determined its birth. And the critical threshold is roughly 2 to 3 times the mass of our Sun. This is called the Tolman-Oppenheimer-Volkoff limit, the maximum mass a neutron star can support before gravity overwhelms neutron degeneracy pressure. Most magnetars are probably below this limit. They formed from stars massive enough to create neutron stars, but not so massive that the core exceeded the critical threshold. These magnetars will never become black holes. They'll simply fade. The magnetic field will decay over millions of years. The rotation will slow to once every several seconds or minutes. The surface will cool to near absolute zero. What remains is sometimes called a black dwarf, though that's a misleading term. It's not related to white dwarfs. It's simply a cold, dead neutron star, still incredibly dense, still warping space-time, but emitting no detectable radiation, just a dark sphere floating through space, invisible unless something passes close enough to feel its gravity. But some magnetars might be right at the edge of that limit. If a magnetar's mass is very close to the maximum, it might be supported only by the outward pressure from its magnetic field and rotation. As these energy sources decline, the support weakens. Eventually, the magnetar could cross the threshold. In an instant, gravity would win. The neutron star would collapse into a black hole. This process wouldn't be dramatic from the outside. No explosion, no flash of light. The magnetar would simply vanish, replaced by a tiny black hole perhaps 20 miles across. Any magnetic field would disappear. The rotation would become irrelevant. The object would transform from one extreme state to another. We've never observed this transition. It might happen too quickly to catch. Or magnetars might lose enough mass through particle winds and radiation that they safely fall below the critical threshold before collapse becomes possible. We don't know for certain. The theoretical models give different answers depending on assumptions about the equation of state, the relationship between pressure and density in ultra-dense matter. There's also the possibility of accretion-induced collapse. If a magnetar exists in a binary system, it might gain mass from a companion star. This additional mass could push it over the limit. The neutron star would collapse into a black hole while still relatively young and active. This scenario might explain some mysterious transient events astronomers have observed. Some researchers have proposed that we might detect these collapses through gravitational waves. As the magnetar contracts rapidly into a black hole, it would emit a brief burst of gravitational radiation. Detectors like LIGO and Virgo might pick up these signals if they occur in our cosmic neighborhood. So far, nothing definitive has been detected. But we're still in the early days of gravitational wave astronomy. The universe might contain billions of dead magnetars scattered throughout galaxies, invisible remnants of violent pasts, too cold to emit radiation, too small to notice unless you're right next to them. And mixed in with them might be small black holes, the final form of magnetars that cross the threshold. We'd have no way to tell them apart from a distance, But regardless of which path a magnetar takes, its reign of terror is temporary. 10,000 years of violence, then millions or billions of years of silence. The universe's most extreme objects are also among its most transient. They blaze brilliantly and briefly, then vanish into darkness, remembered only by the scars they left on space-time itself. Physics has limits, not because our theories are incomplete, though they certainly are, but because nature itself has boundaries. There are maximum temperatures, maximum densities, maximum field strengths beyond which the laws we know break down completely. Magnetars push us right up against several of these limits. Start with magnetic field strength. In theory, magnetic fields can increase without bound, but practically they can't. At around 10 to the 17th Gauss, the magnetic field becomes so strong that the energy density exceeds the mass energy density of matter itself. The field would curve spacetime more than the object creating it. It becomes gravitationally self-interactive, generating its own gravity. This is called the quantum critical field strength. Magnetars reach fields of 10 to the 15th Gauss. That's only 1% of the quantum critical limit, but it's close enough that quantum effects become important. Virtual particles in the vacuum respond to the field. Photons split. The vacuum becomes polarized. We're in a regime where quantum mechanics and general relativity start overlapping, the regime where our theories struggle. Testing physics in these conditions is impossible in laboratories. Our strongest sustained magnetic fields reach maybe 50 Tesla, about 500,000 Gauss. We can generate higher fields in pulse bursts, but only for microseconds before the equipment destroys itself. To reach magnetar-level fields would require energies we simply don't have access to. Nature provides the laboratory we can't build. Then there's density. Neutron star cores reach densities of roughly 10 to the 18th kilograms per cubic meter. That's about 5 times nuclear density, the density of an atomic nucleus. At this point, neutrons are packed so tightly that they're touching. There's no space between them, and we don't fully understand what happens when you push even further. Different theoretical models give different predictions. Some say the matter remains neutrons, just compressed even more. Others say quarks deconfine, creating quark matter. Still others propose exotic phases with names like color superconductivity or pion condensation. We have equations, but no data to confirm which equations are correct. Magnetars and neutron. Stars generally are testing these theories naturally. Gravitational time dilation near magnetars approaches limits too. Time runs 30% slower on the surface compared to distant space. That's not close to the extreme time dilation near a black hole's event horizon, but it's significant enough to measure relativistic effects with precision. Any deviations from general relativity's predictions would show up in magnetar observations. Temperature is another frontier. When magnetars form, their surfaces briefly reach temperatures of 1 billion degrees or more. That's hotter than any star's core. At these temperatures, thermal photons have energies comparable to electron rest masses. Particle-antiparticle pairs pop into existence from thermal energy alone. The distinction between matter and radiation blurs. Rotation provides yet another limit. Young magnetars can spin at several hundred rotations per second. At these speeds, the equator is moving at significant fractions of light speed. Material at the surface experiences enormous centrifugal forces fighting against gravity, spin much faster, and the magnetar would tear itself apart. We're seeing objects at the physical limit of how fast something can rotate without disintegrating. All of these limits converge in magnetars: extreme magnetism, extreme density, extreme gravity, extreme temperature, extreme rotation. Nowhere else in the universe, except perhaps inside black holes where we can't observe, do so many extreme conditions exist simultaneously in one place? Magnetars are nature's extreme physics laboratories, and they're telling us something important. The universe can reach these limits and sustain them, at least temporarily. Our theories predict collapse, instability, breakdown, yet magnetars exist. They're stable or stable enough. This means our understanding, while incomplete, is at least approximately correct. We're on the right track, but there are hints of new physics lurking in the data. Small discrepancies, behaviors that don't quite match predictions. These hints might be measurement errors, or they might be the first cracks showing in our current theories, pointing towards something deeper. Every observation brings us closer to knowing which. Since 2016, astronomers have been tracking something peculiar and fascinating. A repeating fast radio burst source, designated FRB 1212, sending out radio pulses at irregular intervals from a distant galaxy. Unlike most fast radio bursts that fire once and disappear, this source keeps pulsing, sometimes dozens of times in an hour, then silence for days, then bursts again. The pattern is chaotic, but it's not random. Statistical analysis shows structure hidden in the noise. The bursts cluster during certain periods. They avoid others. There's a roughly 16-day cycle buried in the data, though not every cycle produces bursts. Whatever creates these signals is operating on a schedule we don't fully understand. In 2020, researchers tracked the source to a star-forming region in a galaxy 500 million light-years away. The precision location revealed it was near a massive star or stellar remnant. The timing cycle matched what you'd expect from a binary system, two objects orbiting each other. And the best candidate for producing such intense radio bursts remained a magnetar. Here's how it might work. A magnetar orbits a more normal star, maybe a blue giant or supergiant. As they orbit, tidal forces stress the magnetar's crust. When the stars are closest, roughly every 16 days, the stress peaks. This triggers star quakes and magnetic flares. Some of these flares produce radio emission that beams toward Earth. We see them as fast radio bursts. But not every orbit produces visible bursts. The radio beams are narrow, like lighthouse beams. They only hit Earth if they happen to be pointed our way during the flare. Most flares produce beams pointed elsewhere. We miss them entirely. This explains the irregular pattern. The magnetar flares predictably, but we only see the ones that align correctly. Other repeating sources show different patterns. FRB 18091 Stings has a roughly 157-day cycle. It bursts for several days, then goes quiet for months, then bursts again. This longer cycle suggests a different type of system, perhaps a magnetar with a more distant companion or a more complex orbital arrangement. Some scientists remain skeptical. They argue that not all repeaters fit the magnetar model comfortably. The energy outputs are sometimes too high. The burst durations are sometimes too short. There might be multiple types of sources producing repeating fast radio bursts, and magnetars are just one possibility. Alternative theories include neutron star mergers that somehow don't fully merge, or black holes accreting matter in bursts, or even more exotic options involving cosmic strings, though most physicists consider that unlikely. The debate continues because the data is still limited. We have dozens of repeating sources now, but that's not enough to draw definitive conclusions. What's clear is that repeating fast radio bursts are giving us unprecedented access to studying whatever produces them. Single bursts appear and vanish. We can't follow up, can't gather more data, but repeaters let us point multiple telescopes at the source and wait. When the next burst comes, we're ready. We can measure polarization, frequency structure, intensity variations, all in exquisite detail. These detailed observations are revealing complexity we didn't expect. Some bursts show frequency drifting, the radio frequency changing during the pulse. Others show multiple subpulses clustered together. The emission mechanisms must be intricate, involving complex magnetic field structures and particle acceleration processes. If magnetars are responsible, these observations constrain how magnetar magnetic fields are structured. The field can't be a simple dipole, north and south pole, configuration. It must be twisted, braided, with multiple active regions that can produce independent radio beams. This matches theoretical predictions about how magnetar fields evolve over time. And here's the exciting part that drives continued research. We're finding more repeaters every month. As telescope sensitivity improves, fainter sources become visible. Each new repeater adds data points. Patterns emerge, and with enough patterns, we'll finally crack the code. We'll understand not just what creates these bursts, but why they repeat, what drives the cycles, and what it tells us about magnetar behavior. We've traveled across the extremes, from magnetic fields that bend light to densities that warp time itself, from star quakes that outshine galaxies to radio signals that cross cosmic voids. We've seen how magnetars form, how they rage, and how they might eventually die. But there's one truth underlying everything, one realization that changes how we see the universe. We are fragile, unimaginably fragile, and the universe doesn't care. A magnetar 50,000 light-years away can flood our planet with radiation, a flare we can't predict, can't prevent, can't survive if it's strong enough. Our entire technological civilization, everything we've built, depends on stable conditions, stable radiation levels, stable magnetic fields, stable climate. One major magnetar flare aimed our way, and that stability evaporates in less than a second. But here's what keeps scientists up at night. Magnetars are just one threat. The universe contains countless others: black holes, gamma-ray bursts, supernova explosions, asteroid impacts, solar flares. We exist in a cosmic shooting gallery, and we've been lucky so far. Earth has had 4 billion years to develop complex life. In that time, no nearby magnetar has fired at us directly. No gamma-ray burst from a dying star has sterilized our surface. We've dodged every bullet. How much longer will our luck hold? Probability says it will hold for a long time. The galaxy is vast. Dangerous objects are relatively rare. The odds of a catastrophic event in any given year are vanishingly small. But over millions of years, those odds accumulate. Over billions of years, they become certainty. Someday, somewhere, Earth's luck will run out, unless we've already left. The ultimate lesson from magnetars isn't about magnetars at all. It's about the necessity of becoming a multi-planetary species. If humanity remains confined to one world, we're one cosmic accident away from extinction. A magnetar flare, an asteroid strike. Anything could end us. But if we spread across multiple star systems, no single event can eliminate us. Magnetars teach us that the universe operates at scales and energies beyond our imagination. Objects exist that can release more power in a second than civilizations use in millennia. Forces exist that make our strongest technology look like children's toys. And these objects, these forces, they're not rare exceptions. They're part of the standard cosmic landscape. Every time we observe a magnetar, every time we detect a fast radio burst, we're reminded of our place. We're small. We're temporary. We live in a universe that creates and destroys on timescales and scales that dwarf human experience. Stars explode. Black holes collide. Magnetic fields twist space itself into knots. And through it all, life clings to tiny rocky worlds, hoping the chaos passes them by. But here's the paradox that should fill us with wonder. That same violent universe created us. The heavy elements in our bodies came from stellar explosions. The energy that powers life came from a star. The magnetic field protecting Earth came from a molten core, a small-scale version of magnetar physics. We're made from cosmic violence. We exist because of it. Magnetars are not anomalies. They're not glitches in reality. They're reality showing its full range. The universe can be gentle, allowing planets like Earth to orbit stable stars for billions of years. But it can also be catastrophically violent, creating objects that bend and break every rule we thought was unbreakable. And maybe that's okay. Maybe the universe needs both. The quiet regions where life can emerge, and the violent regions that forge the elements life requires. The balance between creation and destruction played out across cosmic time. We're here now, in this moment, on this planet, looking up at a sky filled with wonders and terrors. Magnetars pulse in the darkness, invisible to our eyes but blazing in X-rays. They remind us that the universe is larger, stranger, and more dangerous than we can fully comprehend. But they also remind us that we're capable of understanding. We've detected these objects, measured their properties, built theories that explain their behavior. We've taken the most extreme phenomena nature produces and turned them into science. That's remarkable. That says something profound about what human minds can achieve. So yes, magnetars are terrifying. They're objects of pure extremity, pushing every physical law to its breaking point. They can destroy worlds from light years away. They operate on energy scales that make stars look dim. They represent everything that makes space hostile to life. But they also represent everything that makes space beautiful. The universe at its absolute limit. Physics tested to destruction and somehow, miraculously, holding together. Reality proving it's weirder, more violent, and more wonderful than any fiction we could invent. That's the truth about magnetars. They're not just cosmic monsters breaking every rule. They're proof that the rules themselves are more flexible, more extreme, and more incredible than we ever imagined. They're the universe showing us what's possible when you squeeze matter, energy, and magnetic fields until something has to break. And nothing breaks. Everything transforms. And in that transformation we glimpse the true nature of reality itself.